right, this is one with two capacitors, two resistors. So, anyway, this is Vn. And they have a capacitor or resistor. I forgot the order. Resistor first, then capacitor. And these two are parallel, I believe that. So then they have a capacitor and a resistor here. And here's V out. And I'll just call this R2 and C2. Now, at this point, it really doesn't matter what the values of the resistances and capacitances are. So I'm going to do this, we're going to go through the analysis in a general way with all the unknown, or I should say variables. Then at the end of the day, we'll put in the values of R1, R2, C1, and C2. Everybody with me? So we're in the frequency domain, and with the frequency of closed loop gain, and that would be, this is the closed loop gain. And I'll just put a magnitude here of V out over V in. That's what they want. So now, and this is the way I'd recommend you think about this problem, I'm going to do it in two block forms. I'll call this, whatever the impedance of this is, as Z1, and I'll call this impedance, that is between the negative terminal, or the input and the output, this is simply Z2. You asked about this, do you follow my thoughts as far as why I'm doing what I'm doing? How many do? All right, you follow me on this one? All right, so now, I could go through it. I could say well, the current here would be Vn over Z1. And because that's 0 volts there, no current in, all the current is going up here. So this voltage plus to minus would be I1 or Vn over Z1 times Z2. But because the output is inverted, it would be negative that. Now, I don't care about the negative sign here because this is a frequency domain problem. The input is going to be sinusoidally varying, going negative and positive, as well as the output, so we look at magnitude. Everybody with me on this? Clear? So this is really just going to be equal to the magnitude of Z2 over Z1. That's all it is. There is nothing more to this. You agree? Now, putting the values of Z1 and Z2 in terms of their frequency domain function. So the resistance will always be just resistance. The capacitance here has an impedance of 1 over J omega C1. And I want to be clear, how many see that and understand what I'm saying? In the back, over there, right? That's what that is. Over here, and I hope you can see this, that's R2. This impedance is simply 1 over J omega C2. That's all that impedance is. Now, I'm not done yet, but I'm just putting down the values, the actual values of each individual component. We'll get Z1 in a second. Now, I'm going to make one comment. If you're looking at things online or other supplemental sources for analyzing these type of circuits, they may not use J omega, they may use S. How many have had Laplace transforms somewhere in this class? It's supposed to be everybody. S is really sigma, a real value plus J omega. If you see an S there, it is the same thing as J omega. Now, I don't know how many people have looked online about supplementary material, but that's what I'm trying to just set the record straight. S is not a magic variable, it is just J omega for us. So now we find out what Z1 is. Z1, right here, is simply going to be R plus J omega, in this case, or plus, sorry, 1 over J omega C1. And Z2, I gave you a tip about this last time, right? I'm going to put 1 over the values of each parallel impedance. You remember me talking about this? All right, so for Z2, which is this, I have equal to 1 over, this would be R2 plus J omega C2. Try to make sure you see it. Everybody? Far back, guys. Can you read it? I want to make sure this, can everybody see it right here? Or not? You got it? Okay. Now, what I do for this one is I'm going to multiply top and bottom by R2, the denominator and the numerator. So now I get this is equal to R2 over 1 plus J omega C2 R2. And I want to do that because I want a 1 plus J something. That's what I want, so I can figure out where this term goes to 1. It's called the 3 dB point. Everybody with me on this one? Now, just put this in this equation. I think I have room here. So if I look at this, Z2 right here is going to be R2 over 1 plus J omega, and here it's C2 R2, and it's divided by Z1. This is Z1. Follow me? All right, so Z1 is going to be divided by 1 over, and here you got R1 plus 1 over J omega C1. Y'all agree with this? Maybe I should have done the next step right here. If you look at this for a second, you can see, well, this isn't exactly the way I like things laid out, right? You can see that this is a little troublesome. You don't know what to do with that. Everybody with me on this? So multiply. What I'm going to do is right here, if I go ahead and multiply top and bottom by J omega C1. Can everybody follow me on this, class? I want to make sure you can see it in the far back. Everybody, I want to get rid of this J omega C1, and in doing so, I'll be left with a 1 there. I'll do it down here. So I have R2 over 1 plus J omega C2 R2, and then I'm going to have J omega C1 over 1 plus J omega C1 R1. You good with that? Everybody? Let me show you a few tricks. Now when you see that, it first of all, it doesn't look like the other ones because of this stuff. So here's how you evaluate these things, is the type of filter. Listen, first you let omega be 0. You do this at the extremes. We're going to look at omega equals 0 and omega equal infinity. You all follow me, class? So at omega equals 0, well, if you put a 0 down here, it's 1. A 0 here is 1. A 0 here is 0 times anything is 0. It is 0. Do you all follow me? Now take the limit as omega goes to infinity. As omega goes to infinity, what do you see happening? Just look. I have an omega squared downstairs when you square it. Isn't that right, class? When omega is going to infinity, the 1's go away. You effectively have an omega squared downstairs. You only have an omega up top. It's going to 0. You with me? So that tells you at the extremes that's going to 0. Now, if this was omega, you know at 0 it's 0, and at infinity it's going to be 0. But somewhere in here, it's going to do this. And that's just an approximation. Do y'all follow me? Somewhere in there. So I start looking at this. Listen, this is important. And I look at where these frequency breakpoints are. Here's one right here, and here's one. These are the 2 points where they're called poles in the bottom, in the denominator, where if I can find those values, I know the top one's just going up as an omega, right? So it's proportional with omega, but it's real important. In the very beginning, I might as well just say this, in the very beginning, you're gonna have omega C1 R2 as the weight upstairs. So as you increase omega every decade, it's going up 20 dB. Follow me on this? How many do? You know it's going to linearly increase. You can't help it. Downstairs, neither one of these two is going, I mean, this value, the omega C2 R2 and the omega C1 R1, will not, I call it turn on, they will not be of the order of 1 and affect things until you get past these break frequencies, right? Now listen carefully. So it's going up at 20 dB per decade. That would be down here. I'll fill in the actual values in a second. But something happens. All of a sudden, one of these two values, just listen now, one of these two values goes to 1, so omega goes up. You all follow me? At that frequency, then these things start going down at 20 dB per decade. This was going up at 20 dB per decade. They cancel and it's flat. Listen to me now. So it will be flat, like this. We'll get this frequency in a second. Then, when all of a sudden, the second one, I don't know which one it's going to be, when the second one all of a sudden becomes of the order 1, how many understand this, what I'm talking about right here? You follow me on this? You asked this. You three, yes? Okay, I mean, like poker faces. You can't get an idea what you're thinking. Everybody with me on this? All of a sudden, then it'll start going down by an additional 20 dB per decade. That's here. Everybody with me? This is called a band pass filter. Later on, I can't say when, but you're probably in your senior year going to be dealing with low pass, high pass, and band pass filters. How many have been doing that somewhere? What, is it a lab or where?
Systems. Okay.
Just systems?
Yeah.
How many have had systems or are taking systems now? Do you remember this terminology? Band pass? Low pass, high pass, band pass, or not? No? You guys do? You're going to get it apparently in systems, but you should see this in your laboratory work at some point, I think. You're going to get it. You have to have a senior lab that has this stuff, I think. Mechanicals for sure. I don't know about industrial or an aero. Your aero, you surely have to have this, I think. All right, now, hear me on this. So the question is this. How do we find out where these frequencies are, right? You don't know just by looking at that. So what you have to do is evaluate these two frequencies. Everybody hear me on this? You don't understand it. I have to figure out where that goes to 1. You with me? So I put omega C2 R2 equal 1. Now listen, you with me? Now I rearrange things and I see omega is equal to 1 over R2 C2. And I'll just call this omega 1. That is the frequency where that would become 1, and that pole would all of a sudden become dominant, start affecting things. With me, class? That would be an omega, that would be radians per second. If you wanted the frequency F1, it would be 1 over R2 C2 times what, or divided by what? Class?
2 pi.
By 2 pi. How many see this? The relationship between omega and F is 2 pi. So if you have omega, you divide by 2 pi, you get the frequency. It's more common in hertz or cycles per second. So you would divide this by 2 pi. Now I'm asking somebody a question. I need somebody to do this for me. Can you tell me what that frequency is? I have R1 and R2 somewhere. Well, maybe I don't. I guess I don't, but you have them in your book. We'll put them up here. What is R1? R1 is 10K?
R1 is 5K.
5,000, 5K ohms. What about R2?
3K.
3,000. What is C1? 20 microfarads. And what is C2?
1 microfarad.
All right. Y'all with me? So, can you give me F1? Or I could better call it F2 because I got C2 there. I'll call this 2. What is this? What is F2? 1 over C2, R2, 2 pi. Anybody? I just need you to know the number. 200 hertz, is that right?
Radians per second.
Omega, give me an F, divide by 2 pi. I don't want 1 over R2C2, divide that by 2 pi, because I his answer will be in F, in hertz. Say again? Anybody confirm that? 31.8, is that what you got?
I disagree.
You disagree. I disagree, because you disagree. What is it? 314, anybody confirm that? My life.
53. The second frequency is 53.
C2 is 10 to the minus 6. R2 is 31.8.
It's 53.
Let's try this approach. What did you get?
I got 53.
How many got 53? God, this is scary. This is a class full of future engineers. We can't do basic division.
1 over R2C2 is 333.33.
Divide that by 2 pi.
Is 53.
Ah, I'm going to go with that.
There we go.
Yeah.
53 hertz. Now, and I might as well just say, if you look here, can everybody see over here, that frequency, which I'll call F1, would be 1 over C1 R1 divided by 2 pi. I'm going to just put it here. I need these values. So this is going to be 1 over 2 pi, and this is going to be C1 R1. All right, let's try the old mathematics again. Let's get past basic math. What's that value based on those values, or your book's values? Maybe you can't read my writing, is the problem.
1.59.
Yes.
What?
1.59.
1.59?
Yeah.
Wow, that's really low. Is that right? Okay. All right, so hear me, and you can tell me if this is what you saw in solutions. This frequency is the low frequency, which would be 1.59 hertz. If this is, I'm not going to put it in omega, I put it with F, because that's the way almost everything is. So 1.59 hertz. This frequency where the second pole comes in is 53 hertz. Now, what they're probably going to ask for is the bandwidth. And the bandwidth here is just going to be 53 hertz minus 1.59 hertz, or whatever that is, 50 point what? It's about 50 hertz, right? Roughly? Is that what they have? Does he ask the bandwidth in that one? I'm just curious. He has to. He doesn't ask for bandwidth?
No, what's the cutoff frequency?
Does he show this plot that I sketched?
Yes, but it's like a bell curve. It's not flat.
Yeah, this is.
All right, all right, I'm showing you the Bodie. He'll do this. He'll have something like this, right? All right, his is the exact values. Don't worry, usually your Bodie plots. All right, those would be the cutoff frequencies. Listen to this last point I'm making, it's very important. If you were asked the actual gain value at a specific frequency, you hear me on this one? If they said they wanted it F as 25 hertz, somewhere in the middle, then you would come over here and you would replace omega with 2 pi times 25, or 100 pi. Then you would evaluate that. Now remember, there's omega upstairs too, there's a C1, there's an R2 here. You would evaluate that and you would get the exact value. You all follow me? Give me a show of hands if you do. These things are not that tricky, but the real trick, if there is one, is to manipulate it into the form where you have poles and zeros and you have 1 plus j something, 1 plus j something. That will give you all the information, everything. But if you just have it like I did here, you look at this and it's, I don't know. Follow me? This, you know. And does he have 1.59 and 53?
You can't see it.
What do you mean?
It's cut off.
Isn't it right below that in the next problem?
He also used the wrong resistance. He used 5K instead of 3K for the second resistor, so they're all a little
He
small.
swapped the resistor
No,
values?
they're both 5K in here.
They're both 5K?
But they're not in the book. So.
The book has different values, but he uses 5K. All right, well, then he messed up.
Yeah.
But you get the idea. Does everybody understand the method? It's important you understand why I'm doing what I'm doing. The whole idea is to get these terms into a form where you can evaluate what's going on. This I can evaluate. I can't evaluate that easily. Y'all with me? Now that's the key thing. And let me just be frank about it. In the real world, if you get some wacko function that you come up with, for whatever reason, you want to know what's going on, you don't have to mess with that. Just, you got mathematical programs, plot the thing, be done with it. That's my advice in the real world, because I'm supposed to give you practical advice. In the working world, I get a wacko function, I don't mess with it. I just plot the magnitude of that, and I usually use MathCAD. Unless it's really complicated, then MATLAB or Octave. I think I've told this class this, remember, Octave is free. It does everything MATLAB does, only a little slower and with not as much pizzazz. I'm gonna use MATLAB in here. I thought everybody had to in engineering. Octave is free. Remember, free is good. Python is free. Do y'all use Python? No? Oh man, you get in the real world, Python, Octave, big companies will use MATLAB. All right, another question. Any other questions about this first, class? Yeah. Hold on, people, let him talk. Yeah.
If you want AV at a specific omega.
What?
If you want your AV value at a specific omega, how do you get rid of the J's again? Do you have to square
All right.
everything?
Just for everybody's sake, I'm gonna do it right here. Anytime you have a complex number, anytime, if you have this, and I'm showing you this in a complex plane so you fully appreciate it. This is the complex plane, so it's really called the S-plane. This would be the real axis, and this is the imaginary axis, or the J-axis. Whenever you have a number, doesn't matter what it is, it's got a real and imaginary part you can plot. Let's just say I have a point A here, and A is going to have a part here that's going to be, I'll call it alpha, and it's going to have a height here, beta, all right? So A is going to be equal to alpha plus J beta. Y'all follow me? Now, the way I think about this is this line right here is the magnitude of A. Just think about this in terms of right triangles. With me? So if this is alpha, one side, and this is beta, this value A would be the square root of alpha squared plus beta squared. You all follow me? This is how you get a polar magnitude. Can you see it there? All right, how do you get the angle? Let me ask this for everybody's sake. Don't blow it up yet. If this angle is phi, how would you as engineers get that angle? Just tell me. Anyway, a tangent would work, a cosine, right? A sine, you've got all three sides of a right triangle. I would go opposite over adjacent is equal to the tangent of that angle, or inverse tan of opposite of over adjacent gives you that angle. In a polar form, you get magnitude and angle. In a rectangular form, you get real and imaginary. Did that answer your question? So in other words, if you have 1 plus j omega RC, the magnitude would be the square root of 1 plus quantity omega RC squared. Square root of that. Follow me? Yeah, you have to, but don't square the j. That's what I see. Square j is you don't do that. You just take the magnitude of the horizontal, magnitude of the vertical, square them both, take square root. That's it. Got it? All right, any other questions about this? I have one thing to do before you get your quiz that you're so anxious for. And that is talk about diodes for 1 second. Now, did you think op-amp's operation was difficult? Yes or no? No. Thank God. Engineers still think well. All right, the second thing is diodes are even simpler. Shocking. But you have to pay attention. which is the hardest thing in this class to get. Because there's, I don't know, what do you guys watch, TikTok or something? I don't know anymore. What do you want to do? It used to be fantasy football.
I look over.
How many have had diodes in here? I gotta ask you. Surely mechanicals have. No?
What was the question?
Have you been exposed to what a diode is? Thank
That's the one thing I
All right. Hear me. I may alter that quiz based on the attention I'm giving. This is the symbol for a diode. That's it. Kind of looks like an op-amp, but it's not. You'll notice there's only one input, one output. Y'all hear me? What does a diode look like? It looks like this. If this is called the voltage on a diode, VD, anytime that diode has a positive voltage, which is called its forward bias, current flows and it looks like zero resistance. Do you hear me? Anytime the voltage has an opposite polarity, or VD is negative, trying to push current this way, it is zero current, or it looks like an infinite impedance. In other words, this is called a switch. Now, in your mechanical and aerospace engineering fields, you have something called a check valve. How many know what that is? What does a check valve do, in your words? It allows water to flow only one way. It's a ball, basically, contained in a fixture that will allow it to move up and back, and if it tries to move one way, it'll close off the flow of water, and the other way, it's not going to. Basically, water can get around the check valve ball. Right? It's the same principle here in electrical engineering. So what they'll say is this: if I looked at the diode voltage right here versus the diode current, ID, and I'll put it this way, this would be ID. This is called an ideal diode. It does this. It is absolutely, no matter what the voltage is, if it's negative, zero current, and at this point it spikes to infinity. In other words, it would look like a short circuit if you try to put current one way. Now this is, a lot of people don't like this. It doesn't look like it's a linear system. It isn't. This is a non-linear element. Y'all hear me? So the next logical question is, what good is that diode? So how many know you got AC in the wall, it varies like that, the voltage and current, and you would like to get DC out of that. You would like it like your car battery, constant voltage. So what do? This is my last point. It's the simplest possible thing. They will have a transformer, and I'm going to say this one is 120 volts, and put the dot here, make N equal 1, and N over 2 equal 2. So then you would get plus 200, you would get basically 240 volts here. Y'all follow me? This is going to have a 2 here that didn't show up. So then, let me just finish this thought and you'll get it. This is the only thing I absolutely want to get to today. I'm going to say this voltage in the secondary is simple. This is a 2 here. It's plus to minus 240 volts. But remember, it does this, right? Oscillates up and down, sinusoidal. Then you do this. This is called full wave rectification. really what I should do is before I do this, give me 1 second, I'll do something else. Suppose I just have a voltage source as such, and I have a diode as such, like this. And then I have a resistor as such, R. And I want to find the voltage at the load here. And I know this voltage is going to be, I'm going to just say it, it's going to be 100 cosine of omega t volts right here. So if you looked at the voltage waveform on the input, this would be the actual source voltage, 100 times cosine of omega t. It would be doing this, with a peak value of 100 volts and a minimum value of minus 100 volts. Then, if you look at the voltage on the load, now listen, anytime this voltage is positive with respect to the bottom here, current flows through here as if that diode doesn't exist. Y'all hear me? So all the voltage will be there, so it'll do this. It'll basically, it'll be absolutely tracking this. It'll look like that. But then, at the point, at this point right here, where all of a sudden this becomes negative, this positive, it tries to drive current this way, none of that current can go through the diode. You all hear me? So it does this. It's absolutely nothing, then it hits this point, and it comes up, then absolutely nothing. This is called half-wave rectification. Now, and I'm not going to have time to do this, this particular circuit will do full wave rectification. When this is positive, this is negative, current will flow this way here, this will become positive. It'll come through here, and I actually drew this wrong. This is drawn upside down, but this is plus minus. This would be positive, current would return here through this. Basically, it would flow here, here, and then here. It can't flow that way, it's going against the arrow. Then when it flips, basically when this becomes negative and this becomes positive, all the current will still flow in the same direction and you'll get full wave rectification. You will appreciate this once you go through some. This is an ideal diode. I'm going to give you some homework problems for Monday about this. It is very simple, but you must do these homework problems. Otherwise, I can't go on with the lecture the way I want to on Monday. And Wednesday, we're jumping into bipolar transistors that are more complicated. So you will see this. All right, everything off your desk.